Hello there, my name is David Liu, and I'll be presenting on the fourth lab of Introductory Physics 1 at Georgia Tech titled Oscillations. The purpose of this lab was to capture the video of a motion of an oscillating spring mass system, apply motion physics principles, and compare our observations of that system model to a computational model. This will allow us to predict the motion of a similar system, such as the extreme rope sports example discussed in the pre-lecture video. The main result of this lab is that the harmonic motion of the computational model closely matched that of the experimental model, albeit with some discrepancies. The velocity update and position update formulas were of importance in this experiment as they allowed us to iteratively calculate the predicted motion one step at a time. These and other physics formulas from other fundamental principles in the course were used in this experiment as well, namely the momentum principle, the energy principle, and the period for a vibrating spring related to a concept known as Hooke's law. These were used to find the spring constant. The system encompasses the spring mass system and Earth, whereas the surroundings include nothing. Because all of the forces were within the system, the work done on the system by the surroundings was assumed to be zero. A pre-recorded video of a spring being stretched and then released was used as the basis of the observational model. Although this video of spring mass d uses a small mass attached to a spring rather than a rope, it is still useful in achieving the overall objective of the lab. In Tracker, the coordinates were selected as a point mass for the duration of 75 frames, or 7.1225 seconds. The calibration stick, also found in the pre-lecture reference video, was 0.7 meters in length away from the origin or where the spring was attached. It was assumed that there were no dissipative forces. The previous formulas and physical principles were essentially translated into code. This Python was needed to correctly calculate the spring force, which we found from the period and mass. The related length of the relaxed spring was also found from this equation, by solving for L0 equal to the magnitude of the initial length of the spring minus the mass times acceleration of gravity divided by the spring stiffness. Each of the variables was defined, and then the physical formulas on the right were shown and translated into code on the left. The force of gravity equal to the ball's mass times the gravitational acceleration in the negative y-hat direction. The potential energy of the spring, or 1/2 of k times the change in the length of the spring squared, or s, and the kinetic energy, 1/2 times of the mass times velocity squared. L is equal to the mass's position minus the spring's position at a given time. When s is equal or greater than 0, the spring is stretched, and when it is less than 0, it is compressed. The system energy is then calculated, each of which was the gravitational potential energy, the spring potential energy, and kinetic energy. This process was repeated or iterative so that at the new time or designated time later, the time was advanced. The code block on the right shows the code required to plot the oscillating positions as a graph with the rate factor set to 15. This count was set to be 0.095 or 1 divided by the frame rate of the video. A graphical representation are depicted here, inserting the x and y positions generated from Tracker as a CSV file into the Web VPython program produces the following graph. This will be elaborated upon in the discussion, as the red sphere refers to the experimental model, while the blue sphere represents the experimental position. Though the conditions we were presented at first were idealized, a variety of errors may have been introduced into our experiment. These include improper calibration, which would fall under the category of instrumental errors, as well as a lack of accounting for actual forces in the real world, such as air resistance and drag. This could have resulted in fluctuations that may at least partially account for the disparities observed between the computational model and our physical observations. Addressing what does it mean, energy does appear to be conserved, as the orange line delta E is equal to 0 for the duration of the time interval observed. However, although the change in energy of the system is close to 0, it may not actually be 0, but rather several magnitudes of order less than the changes in the other energies. The average periods, or time between the peaks, are also displayed here, and the spring is supposed to exhibit some pendulum-like character in the x direction, and as such it took slightly more time to complete one cycle than in the y direction, where the force of gravity would be enacting upon it. The Tracker analysis also appears to display sine waves for both the xt and yt graphs. Moreover, although it is a common misconception, increasing this amplitude should not affect the period of the spring because the restoring force would increase the acceleration of the mass. So in short, these data have demonstrated that there may be slight differences between what is predicted and what is observed, and this divergence can be accounted for in the differences between the theoretical simplification and real-world conditions. Thank you.